Okay, so we're looking at energy principles applied to rigid bodies that may rotate and translate. The last thing we'll look at before we look at some examples is what happens when we have a torsional spring. So a torsional spring as opposed to a linear spring will counteract rotation or enhance rotation, depending on whether your spring is extending or shortening or compressing. So just like in the linear world where you have your spring force sort of opposing the extension or the compression, so we have something like F the force equals minus K, the spring constant, multiplied by X, the distance the spring has moved relative to its, or the displacement of the spring relative to its equilibrium position. We have a similar term for some torsional springs. For a torsional spring, we'll have the moment being minus K, which is the torsional spring constant, times the angular displacement, theta, the angular displacement, theta. Okay, and the kinetic energy of the torsional spring, or the elastic energy of the torsional spring, not kinetic energy, will be given by a half K theta squared, where again theta is the angular displacement and K is my spring constant, but spring constant as it relates to moment or torque and angular displacement. Now let's look at some examples. Alright, so in this example we have a motorcycle, and each wheel of the motorcycle has a mass of 9 kilograms. You're given the radius. You're also given the moment of inertia, and typically when you're not given a particular axis, if they say it's a moment of inertia I is such and such, then you're talking about the moment of inertia about an axis through the centroid. You're also given the combined mass of the rider and the motorcycle, not including the wheels. We are also told the motorcycle starts from rest, so that's usually a key word, starting from rest. You know that what your velocity is 0, and you're given a constant couple supplied by the engine on the rear wheel, and some assumptions here. Assume that the wheels don't slip. So where's that going to come into play? We'll see. And what horizontal distance b must the motorcycle travel to reach a certain velocity? So what distance b must the motorcycle travel to reach a certain velocity, a velocity of 25 meters per second? So why would we want the energy approach here as opposed to the Newton's second law approach? Well, this problem is asking for distance and it gives you velocity, and you have some masses here and moment of inertias. So if you think about the second law deals with force and acceleration. So in order to find the distance, we would have to first figure out what the accelerations are, then we'd have to apply our relationship between acceleration and distance, which would involve integration in most cases if your acceleration is not constant. Well, integration in all cases. If your acceleration is not constant, then it gets more complicated. So let's bypass all of that. We know energy directly relates velocity in terms of the half mv squared. It directly relates the velocity to the work done by forces, which is what? Force integrated over distance. So we can figure out what these forces are, can't we? What forces are in play here. We want the distance and we're given some velocities. Alright? So let's move on. So I'm going to draw my free body diagram. I still need to see which forces are doing work and which forces are not doing work. So I have all my vertical forces here. Of course, AY is my vertical reaction, my normal reaction. Then I have my weight forces. But all those vertical forces are not doing any work. Why? Well, the bike is not moving up, nor is it moving down, right? How about AX, BX? Are they doing work? Well, think about the point where they're acting. Does that point have a velocity? Is that point actually moving? And the answer to that is no. We know that when you have rotation of a disk, for example, on a plane, the point of the disk that makes contact with the ground has zero velocity. So AX is acting on a particle or a point here that has zero velocity. So neither AX nor BX are doing any work. Now what is doing work? Well, remember, if you think about the engine here, or the torque that's being supplied by the engine here, is causing some rotation of the wheel. So that torque is doing work, or that couple is doing work, because you have a couple acting on the wheel and it is causing rotation of the wheel. Why is it not shown here? Well, that couple is internal. It's an internal force. So if I break up the diagrams here, I can show the couple acting on the wheel, and of course an equal or opposite couple acting on the body of the motorcycle. Now why is this one doing work and this one not doing any work? Well, the equal and opposite couple is not doing work because the bike is not rotating. The bike and the driver, unless he was doing a wheelie, but the bike and the rider are not doing a rotation right now, right? So we have a translation there. So the work done by all the forces on your body would simply be zero for everything except for the couple acting on the wheel. Now that work done is what? Magnitude of the couple times the change in the angle. We started from rest, so we can say the theta 1, the first angle, is 0. The second angle would be given by the arc length divided by the radius. The arc length that has been traversed if you move a distance b. And clearly if you move a distance b, the arc length that has been traversed is b. So my angle is b divided by r. So I have the total work done by my couple, m times b over r. Remember, r is given. Equals the change in kinetic energy. Now what's going on here? The kinetic energy is given by, for a body that's rotating and translating, it's given by the half mv squared term plus the half I omega squared term. Well, both wheels are translating and rotating, so that's where this comes from. And the body itself is the rider and the bike frame have a kinetic energy of half mc v squared. So we have equation 1. What are we given? We're given the moment, constant couple here. We're given the mc. We're given the r. We're given the mw. We're given the velocity. The velocity was 25. We're also given the moment of inertia here. So the only things we don't know in this expression are b and omega. B and omega. But recall that I know how the velocity is related to omega, right? Omega is just the velocity divided by the radius. So I can eliminate omega from that expression by substituting omega equals v over r. Then I get an expression where the only unknown is b. So finally I can plug in all my values that were given. IRM, the masses and the couple, and etc., the velocity, and I can figure out what my distance b is equal to. In the next example, I have two links connected to a collar here, a torsional spring at one end. We're told that the system is released from rest, so immediately we know that what? The initial velocity is 0. At position theta equals 0, here's my theta angle, and also we're told to neglect friction, and we're asked to find the angular velocity omega of the bar AB, so there's bar AB, as a function of theta. Omega, the angular velocity of the bar AB, as a function of theta. We're also told that there's a torsional spring at A that exerts a clockwise couple k theta on bar AB. So the system is released from rest. So what would you expect? You'd expect this color to sort of slide down a little bit, and point B here to move to my left, right? But let us draw the free body diagram, okay, and identify which forces and couples are doing work, and which are not. So this is my free body diagram of the entire system. Right, I have the mass, the weight of the color, the weight of each bar, the normal reaction from the axle onto the bar, and the reaction forces at the pin A, as well as that spring force that we're told is occurring. So I'm going to apply my conservation of energy principle, which is really just another way of saying I'm applying the work energy principle of work and energy, right? So now the conservation of energy tells us that what? The work done by, the principle of work energy tells us that what? The work done by your forces is a change in kinetic energy. Since we have just weight forces acting here and spring forces, these are all conservative. So we can immediately just use the conservation of energy principle, which tells us that the total kinetic energy and potential energy, the total of those must be the same between states. Alright, so if I find the kinetic energy of the bar AB, I'm going to use a half IA omega squared term. Why just that one? What happened to the half mv squared term? Well, I don't have to worry about it because it's rotating about a fixed point. So I here is going to be the moment of inertia of an axis through that fixed point, right? I can use the parallel axis theorem, okay, if I know the moment of inertia for a slender bar about an axis through its centroid, right? So I can do that, and this I here, if we look in the tables, this I here will be given by 1/12 ml squared, and then the distance between those axes, between the bar centroid and A, would be half L. So I end up with this expression. How about bar BC? Well, BC has some translation and rotation. It's not rotating about a fixed point, so I can't just use the half I omega squared term. I need to use the entire kinetic energy term, which is the half mv squared term, translation plus half I omega squared term. This I here, very important to remember that this I here is a moment of inertia about an axis through the centroid. Alright, so I can plug all of that in. For the color has no rotation, so we just have to worry about the translation term for its energy. Okay. Then I can obtain, so I have all my kinetic energies. Now I want my potential energies. Well, I have a spring, then I have several weights. Alright, so if we reference our potential energy to some datum, or weight potential energy, then I can have the potential energy due to the weights being just my mgh term, and we see we get mg a half L cosine theta for bar AB, for example, because remember the weight is acting to the centroid, and the distance from the centroid to the vertical distance from the centroid to point A, if you play with the geometry a little bit, you will see that that vertical distance is L cosine theta. L over 2 cosine theta. I have L over 2 here, and this is theta here, right? So the vertical distance here is L over 2 cosine of theta, which is located right there. And we can keep going with others, and we get very similar expressions. We also have the spring, right? So the spring has some potential energy as well. It's a half k theta squared. So now I have the kinetic energy terms and the potential energy terms for all the components in my system, and now at an angle theta, when the system is at an angle theta. I also can figure out what the terms are when the system is at an angle 0. And then I'm going to apply my conservation of energy. So at an angle 0, my potential energy for the two bars would be 2 mgl, and for the color would be 2 mcgl, or mcg times 2l.